esteemed resource person, Dr. Kannan Srinathan sir is an assistant professor at IIIT Hyderabad. He is an alumnus of IIT Madras, where he did his PhD in computer science and engineering. His research interests include cryptography, distributed computing, and quantum algorithms. He has published over 100 research papers in reputed international journals and conference proceedings. He is the recipient of IBM Outstanding PhD Dissertation Award and Microsoft Young Faculty Fellowship Award. I invite our person, Mr. Dr. Kannan Srinathan sir, Assistant Professor, Department of CSE. Sir, welcome.
Thank you. Thank you for the introduction. Good afternoon to all of you. Sorry for the delay. I got stuck in traffic near Gachibowli. Next 45 minutes or so, we'll talk about quantum cryptography. Before that, let's introduce quantum computing in one slide. So, quantum computing promises a lot as well as is a challenging field. For instance, if you are a user, it both enchants as well as disenchants you. For example, you can have massive parallelism. For instance, you can superpose all possible inputs in one go. There are two covariant inputs of length n. You can superpose all of them and compute in one shot. So that is very nice. But it also disenchants, because even though you can compute all the threads, when you measure you will get only one. Right? Similarly, if you are a designer, it enchants as well as disenchants. For instance, you can break RSA. We'll see how to break a cryptographic system using a quantum computer in this session later half. But you find that even though it can break, it itself is very noisy because of decoherence, and it is very challenging to build quantum computers that can coherently work with thousands of logical qubits. If you are an applications person, there are very interesting applications. You can do secret sharing, you can do quantum networks, you can also do a Byzantine agreement. But again, you find that the buffering itself is not possible in a quantum machine because of no cloning. Classical networks, you send the packet, you can make a copy of it, buffer it in intermediate, and then forward it and route it. Quantum networks cannot work that way because there is a no cloning theorem. We will prove the theorem shortly, which says that an arbitrary quantum state cannot be copied, and therefore quantum networks cannot work the way normal networks work. However, if you are interested in doing research in the area, then you find that it's a win-win. If you are a user, you find that some things are positive, some things are not. If you are a designer, you find that some things are positive, some things are not. If you are an application oriented, you find that some things are positive, some things are not. But if you are a scientist, it's always positive. Why? Because if you discover something that is positive, that is good news for the world. If you discover something that is negative, that also is a positive discovery. To discover that you cannot do something is also a discovery, and therefore, if you are a scientist, you find that all positives are also positive, all negatives are also positive, and that is a different world altogether, the research world. So this is how quantum computing works in general. Quantum cryptography in particular is extremely special because quantum mechanics appears to have been made for security and security related purposes. Let's explain or discuss why. For instance, Suppose we ask, in the normal classical physical world, if I send some data over the wire, say over some channel, if a man in the middle reads that and then leaves it alone after that, the end recipient cannot figure out whether there was an eavesdropper present in the channel or not. Right? For instance, like you send an email to your friend, there is an eavesdropper in the middle who taps the wire. The end recipient cannot ever figure out whether tapping happened or did not happen because you can always clone. You can make a copy and the eavesdropper will read the copy. The main information will keep transmitting across the channel to the recipient. So the recipient cannot differentiate between the two worlds, one where the eavesdropper is there and other where the eavesdropper is absent. Therefore, you need a lot of mathematical machinery like cryptography to actually preserve the information from reaching the eavesdropper's hands. However, in the quantum world, you find that eavesdropping itself can be detected because you cannot make copies, and if you cannot make copies, you have to read the original. Quantum mechanics says if you read the original, you will affect the original, and such a defect can be detected at the receiver's end, and which means what? Which means even eavesdropping can be detected, which is a very powerful tool with respect to security. Similarly, if you ask next question, suppose you want to do quantum networking and you want to route information across routers, the payload should not be visible to the router. In the classical world, that's not possible. It's not possible to route information such that the information is not visible to the person who is the postman, who's carrying. But in quantum world, it is possible that you are actually sending data along some person, but that person does not know what you are sending. Why? Because in quantum world, unless you measure, you will not know what that is. That's also true in physical world, but in physical world, what do you mean by measurement? So I am sending a letter and you are reading the letter means what? Your light is hitting the letter and coming back to your eye. That is what is meant by reading. Therefore, even in physical world, we are measuring. We are sending light and it is reflecting back from the letter and we are reading. In quantum world, that photon itself is what is going. So if photon is going, you cannot send another photon, hit that photon and find out what its state is without actually affecting that state. And therefore, you find that it is in the quantum world, it is possible that you can send data, but the person who's carrying that data has no idea what is there, because if that person has to actually find out what is there, he has to alter that state because he has to measure. Such a thing will be detected and will be traced back, and therefore he will not do that. If he does not actually measure, even though he carried it, it will not be visible to that person. In normal physical world, if you want to attack something physically, you have to be near it. So suppose I want to attack this computer with a stone, then I have to be in stone throw distance. Right? In digital world, of course, nobody attacks with a stone, but nevertheless, if you want to physically have access to certain devices, it means you are in physical proximity. In quantum world, it is possible to actually access, even physically access stuff without actually being anywhere close by. In fact, even if you are in Andromeda galaxy, as long as your device is entangled with the other device at the other end, you can actually do stuff which changes the physics on Earth, even though you are not even close by. So Einstein did not like this aspect of quantum mechanics, because Einstein called it spooky action at a distance. Einstein felt that for anything to physically interfere with each other, there should be a finite speed, the speed of light, for instance, or speed of causality. If you are somewhere in outer space and the light takes several minutes, for instance, if you are somewhere near sun, light takes about 8 minutes to come from there to here, and therefore Einstein felt whatever you do will affect people on Earth at least 8 minutes later only, not before that. But quantum mechanics says no, even before light has reached Earth, the quantum effects can actually reach. This is why Einstein was not fully convinced about the veracity of quantum mechanics, but then experiments later suggested that what Einstein said is not perhaps correct, and we found that recent Nobel Prize was given for the experiments that actually said quantum mechanics actually has effects faster than speed of light and other things, though you can't use it for communication. In classical world, we all know that integer factorization is hard problem. It's not so the case in the quantum world, and like that you can list several aspects which in the classical world are looking very different from the quantum world, and in the classical world such things require a lot of safeguarding and security solutions. In the quantum world they are inbuilt, and that is what we mean by looks like quantum mechanics is here to help information security. It is also here to disrupt or break information security, because RSA is depending on the fact that integer factorization is hard, whereas in the quantum world integer factorization is not hard, and therefore you need to move to post-quantum cryptography and cannot rely on the security of RSA. So rest of the talk what we will do is we will first look at what quantum mechanics is. I'll give you an introduction to quantum mechanics, just sufficient so that you understand the rest of the talk. Then we'll see a couple of applications. For instance, we'll see how to establish a secret key using quantum mechanics. We'll also see how to break, say, existing crypto systems with the quantum computer. And if time permits, we'll also see the future things like quantum blockchains and speculate what will happen in the future, provided we have sufficient time. So let's begin with what is quantum mechanics and how do you understand the mathematics behind that. So we'll start with an experiment. The experiment will be slightly bizarre, so much so that you need to create new kind of mathematics to model that reality that we see in the laboratory or in real life. That new kind of mathematical model will be given the name quantum mechanics, or has been given the name quantum mechanics as of today. So here is the experiment. So you have a source of light and you have filters, polarizers there, and let's see what the experiment says. Suppose you have a horizontal polarizer A, about 50% of photons pass through. If you have a horizontal polarizer A followed by a vertical polarizer C, no light passes through. However, if you have a horizontal polarizer A followed by an angled polarizer, say at 45 degrees B, followed subsequently by a vertical polarizer C, then about 1/8 of the photons pass through. This is what is observed. Now, what is bizarre here is the fact that, YouTube video was too much. So, is the fact that in classical thinking, things are always monotone. If two people can do the job, then if you have a third person also, the job will get completed. This is monotone thinking. So, for instance, if A and C can block the flow of light, A, B, and C should be able to block the flow of light. That's what we think classically, but in quantum mechanics, it turns out that A and C can block the flow of light, but A, B, and C together cannot block the flow of light. Now, such a thing normally is not possible in classical physics, because if two things are good enough to block the flow of any commodity, three things will be more easily blocked. So suppose water is going, you build two dams, A and B, no water can flow. You build three dams, no water will flow. Right? So if you say milk is flowing and you put one filter, 50% of milk comes out, you put another filter, no milk comes out, you put a third filter, still no milk will come. But when light is flowing, light is a quantum object, and when quantum objects behave very bizarrely. When it's flowing, you put one filter, 50% of things go through. If you put two, nothing goes through. If you put three, again it goes through. So this is such a bizarre thing that first time when I stumbled upon this experiment, I actually required to do that experiment to believe that such things are possible. We don't have the equipment to demonstrate that experiment now in front of you, but there is a recording of the experiment in YouTube, so you can watch it and then you will be able to believe. So browser will before you linking the reading. Background music. Full screen. So screen is your retina. You are focusing. So horizontal progression, 50% of light passes through. Horizontal followed by vertical, no light passes through. Right? Watch carefully when it places in between those two. Outside there is no effect. In between those two there will be a lot of effect. In between these two, at 45-degree angle, light passes through. Right. So see how important this experiment is, because for security, if I have an optical fiber from sender to receiver, I send horizontally polarized light. Right? I shoot photons and put a horizontal polarizer. You receive it with a vertical polarizer. What do you expect? Nothing. Nothing should come out. But if something comes out, what does it mean? If something comes out, what does it mean? It means somebody in the middle is trying to put in some angle. Now only you know what angle to put, and therefore you can see that you can detect if the eavesdropper is there or not with high probability, because the eavesdropper does not know what exactly to do, and there is a chance that the eavesdropper did not put it correctly, and therefore though no light should have come, some light is coming. So therefore, look, this is tailor-made for security, and people use this to actually build security systems. But before that, we promised to give a mathematical model that will predict such kind of behavior of light as well as any quantum object. That mathematical model is called quantum mechanics. You can do it using wave functions. You can also do it using qubits, that is matrix mechanics. You can also do wave mechanics. Both are mathematically equivalent. One uses differential equations, other uses linear algebra. Notice that since Schrödinger equation is a first order differential equation, it is linear, and therefore you can also do it with linear algebra. Computer scientists prefer doing it using linear algebra. Physicists usually prefer doing it using differential equations of the first order. So I will give you the matrix mechanics point of view of quantum mechanics. Quantum mechanics consists of three rules, or three assumptions, or three axioms, or three postulates, whatever you think. First one is associated with any quantum system is a state vector. Alright? So mirror it's projecting the screen, not the full screen. Slide. Right. For instance, if you do an experiment in real life, before doing the experiment, if you ask what is the reality, that reality will be same as the outcome that you get at the end of the experiment, but not so in the quantum world. Suppose you are doing an experiment which has two outcomes. So the system is called a qubit. A qubit is an experiment that has two outcomes. What is the reality before you actually get the outcome of the experiment? It turns out that quantum mechanics says before you actually get the outcome, reality is a superposition of both the outcomes. If there are two possible outcomes. In fact, if there are three possible outcomes, reality is a superposition of all the three. If there are four, then reality will be a superposition of all the four, and so on. And how do you mathematically model superposition? So it is a state vector with amplitudes which are complex. For instance, you can model the photon passing through the filter or not passing through the filter. There are two possibilities. So before you actually put the filter and let the experiment play out, the reality is the photon is in the superposition of passing as well as not passing. So you can call it A times passing plus B times not passing. If you say passing is 0 and not passing is 1, then the qubit is A times 0 plus B times 1, where A and B are complex numbers. So this is the first postulate called the superposition postulate, where it says that before you actually do the measurement, if there are n possible outcomes, a superposition of all the n is allowed. And second is the measurement postulate, which says suppose you actually measure, what is the probability that it will pass through compared what is the probability that it will not pass through? Notice that A times passing through plus B times not passing through is interpreted as A and B are complex numbers. The probability that it will pass through is mod A square. Mod is the magnitude of the complex number, you know, A plus IB, mod is like square root of A square plus B square. Now that mod square is the probability. Mod A square is the probability that you will get 0, mod B square is the probability that you will get 1. So if A times 0 plus B times 1 is measured, then the probability that you will get 0 is mod A square, probability that you will get 1 is mod B square. Where A and B are complex numbers, obviously they should be normalized such that mod A square plus mod B square is 1. Otherwise, probability does not make sense. How does this actually explain or predict the experiment that we did? Notice that when a photon passes through, we said 50% of photons pass through any filter in any angle. Why is that so? That is because photon is A times passing through plus B times not passing through, but it's A and B are random, mod A square plus mod B square is 1. When A and B are random and mod A square plus mod B square is 1, the expected value of mod A square is half. Why? Because there is no difference between A and B, and therefore, when the sum of two equal and identical amplitude is 1, the expected value of the amplitude is half, so probability that a photon will pass through a filter in any angle is half. And therefore, we have a large number of photons, about 50% of the photons will pass through. But second postulate also says that once you measure it, it will collapse to that answer, and therefore once a photon passes through a vertical polarizer, it collapses to vertical. And vertical is nothing, horizontal is orthogonal vector, so horizontal is nothing but not passing through vertical, and therefore probability that a vertically polarized light will pass through a horizontal filter is 0. What is happening if you have a third filter in the middle? Notice that a vertically polarized light can pass through a 45-degree polarizer because passing through 45 and not passing through 45 are orthogonal events. Vertical polarizer can be written as 1 by root 2 times passing through 45 plus 1 by root 2 times not passing through 45. And therefore 1 by root 2 square, that is half, is the probability that the photon which is vertically polarized will pass through 45 degrees. And collapse postulate says once it passes through 45, it will collapse to 45. And what the probability that a 45-degree polarized light will pass through a horizontal polarizer or the other end? Notice that the 45-degree polarizer can be written as 1 by root 2 times passing through horizontal plus 1 by root 2 times not passing through horizontal. And therefore another 1 by root 2 square, that is half probability that it will pass through 45. So 50% will pass through the first filter, 50% of that will pass through the second filter, 50% of that will pass through the last filter. So about 1/8 of the photons should pass through according to quantum mechanics. That is what is the intensity we actually observe. And therefore quantum mechanics is a mathematical model of reality. No matter how bizarre it is, this is what it is. So let's formulate it. So there are three principles involved. The first one is the superposition. It says if you have a reality and it has many possible outcomes, before you actually know what outcome is going to come, the reality is not yet formed. So, for instance, in the classical world, reality is already there before you measure. So, you take a vernier calipers and want to measure the length of some object. That length of the object is already well defined and it is really there. You don't know, you don't have no knowledge of it, and therefore you are measuring. Quantum world is not like that. Quantum world is, you want to do an experiment. Before doing the experiment, the reality is a superposition of all possible outcomes. Only after you do the experiment and get an answer will the reality collapse consistent with that answer. So superposition principle says if an experiment has n possible outcomes, before you do the experiment, reality is a superposition of all those. For instance, if you want to measure whether the electron is in ground state or excited state in a hydrogen atom, before you actually do the experiment, the electron is neither in ground state nor in excited state. It is in superposition of both ground state and excited state. That's the reality. When you actually do the experiment, there is some probability that you will get it as ground state, some probability that you will get it as excited state. What is the probability? It is the amplitude square. So you can write it as alpha naught times 0 plus alpha 1 times 1, where 0 is a ground state, 1 is a excited state. Mod alpha naught square is the probability that you will get it in ground state, mod alpha naught square is the probability that you will get it in excited state. Right? And when you measure, it will collapse. You will get it with the probability distribution and collapse to that answer. Alright? So, with this preamble, we can actually prove the no-cloning theorem ourselves. But before going there is a third aspect, namely evolution. If you leave the quantum system alone, how does it evolve with time? It evolves as per Schrödinger equation, which in matrix mechanics turns out to be, notice that it is a state vector we said, so notice that if it is a qubit, it is alpha naught times 0 plus alpha 1 times 1 can be treated as a vector in C square. C square is C plus C, complex number. So two complex numbers form. So how does the vector evolve with time? Quantum mechanics says that it evolves unitarily. By unitarily, you mean evolves by a matrix multiplication where that matrix is a unitary matrix. What is a unitary matrix? It is a complex matrix such that its inverse is same as its conjugate transpose. So a matrix is said to be unitary if its inverse is conjugate transpose. Now from where did all these complicated things come in nature? Notice that you can view the whole thing also as non-preserving rotation. So nature allows the state vector to rotate in time. You cannot shrink it, you cannot expand it, you cannot do anything else. You can, without shrinking the vector, you can rotate it. So if you do the mathematics of that, you will find that non-preserving rotation, if you do it in reals, it will be a matrix called the rotation matrix. So in the cos theta and sin theta. So you want to rotate a vector by an angle without shrinking it, it's a rotation matrix. But if it is because it's a complex plane, it's not a rotation matrix, it is a unitary matrix. So this is what is quantum mechanics all about. Before you actually conduct the experiment, reality is a state vector which has this probability distributions of all things. If you measure the state vector collapses consistent with your outcome that you get, which is a probabilistic outcome. And third rule is you can always evaluate with non-preserving rotations. This is all is quantum mechanics about. With these three, we should be able to do several things. First thing is we can prove that you cannot make a copy of unknown quantum states. Let's see why. Suppose you could do that. What? As we said, only thing that can be allowed is linear unitary transformations. And to show that you cannot make a copy, all will show is no unitary transformation will make a copy. For instance, suppose U is a copier. What does it mean? It means you take any U, apply it on any state A, and have the answer memory allocated. So A0, U and A0 should go to AA for any A. That's what is meant to be a copier. But notice that if U of A0 goes to AA for all A, we'll show that it leads to a contradiction. What is the contradiction? Consider C, which is superposition of A and B. If C is superposition of A and B, we can ask what should U on C0 do? We know what U on C0 should do. It should go to CC because it is a copying circuit. But U on C0 does not go to CC because U is a linear operator. So C is nothing but superposition of A and B, and therefore U on C0 will be U of AB superposition with 0, which is a linear operator, and therefore you can take it inside. And when you do the operation, you will find that you will get AA plus BB, but U on CC should be this, and this is not equal to this unless AB and BA do not exist. And therefore, in a world where superposition is there, you cannot make copies. If superposition is not there, you can make copies. And therefore, you find that Xerox machines exist. In the classical world where superposition is not there, Xerox machines cannot exist in the quantum world where superpositions are there. So this is the no-cloning theorem. Okay. Because you cannot clone, I can set up a secret key between Alice and Bob. Why? Because you know that the eavesdropper cannot make copies, and here is how the quantum secret key exchange BB84 protocol works. Suppose I encode 0 either as vertically polarized light or as 45 degree polarized light, and encode 1 either as horizontal or the orthogonal of 45 degree polarized light. Suppose I have this encoding. The eavesdropper doesn't know which encoding I am using, whether I am using encoding of B1 or B2. Eavesdropper doesn't know. The receiver also doesn't know. Now I encode like this and send those photons or send those quantum systems. The receiver receives all of them. Since no copy can be made, the eavesdropper is forced to either measure or not measure live. He cannot make the buffering and do something later. He has to directly measure on live. But suppose eavesdropper is live, we'll see how the receiver can actually detect that eavesdropper is there or not there. Let's see how. Suppose I use B1 encoding and receiver also uses B1 basis to measure. Both of us will get the same answer. Why? Because if I set a vertically polarized light and you receive it vertically polarized light, it's positive. If I set a vertically polarized light and you receive horizontal, it's not positive. So not passing through is nothing but not 1. Not 1 is nothing but 0. So if I send 0 and both the sender and receiver use the same basis to measure, you will always get the same answer. If you use different bases, you may get different answer, because if I send a vertical polarized line, you will see with 45 degree angle, it may pass through, it may not pass through, 50-50 chance. So if basis is different, answers can be different. If basis is same, answer is same. Since we know this, and since we know that eavesdropper cannot make copies, what the sender will do is send many qubits in random encoding. The receiver will measure it in random basis. Then sender will publish the basis that was used to create that. Receiver will publish the basis that was used to receive it. Whenever they don't match, we just ignore those qubits. Only focus on those qubits where sender and receiver use the same basis. Now you know that your answer should match. However, if eavesdropper is there is 50% chance that eavesdropper used the wrong basis. If eavesdropper used the wrong basis, see what happens. If sender sends 0 as vertically polarized, eavesdropper measured it in B2 and as 45 degrees. We know that it will collapse to 45 if it passes through, and there is 50% chance that 45 will be measured as vertical, 50% chance that 45 will be measured as horizontal, and therefore there is 50% chance that the answer will become 0, will become 1. If the wrong basis is used, there is 50% chance that the wrong basis is used, and therefore overall 25% chance that the eavesdropper will flip the bit. Therefore, if I keep using the same basis, if eavesdropper is not there should be 100% matched. If eavesdropper is there will be only 75% match. Now you can easily detect whether eavesdropper is there or not there by randomly sampling some of the bits and publishing it. Both the sender and receiver publish it. You check whether the match is 100%. If it is 100%, rest of the bits are your secret key. If it is 75%, you know that eavesdropper exists. You abort the protocol. You have detected eavesdropping. So this is the quantum secret key establishment protocol. With this, you can do several things with quantum mechanics. One of the most beautiful things you can do is, so far we have been working with 1 qubit system. 1 qubit means there are 2 possible outcomes, 0 or 1. Before you actually do the experiment, it's a superposition of those two. Suppose I have 2 such qubits. Then notice that there are 4 possible outcomes. And what quantum mechanics says is, before you actually do the experiment, it is a superposition of all the 4. And that's where things get very, very interesting and bizarre. Suppose I have 3 qubit system. Right? How many possible outcomes are there for a 3 qubit system? 8 possible outcomes are there. What quantum mechanics says? Before you actually do the experiment, the reality is superposition of all the 8. That is, you need to give me 8 complex numbers to describe the system. Suppose I have 4 qubit system. It can give you 16 possible outcomes. So you need to give me 16 amplitudes, complex amplitudes to describe the system. Suppose you have a n qubit system. Right? How many possible outcomes when you measure a n qubit system is possible? 2 to the power n. What quantum mechanics says? Before you actually do the experiment, all the superposition of 2 power n possibilities is reality. So you need to give me 2 to the power n complex numbers to describe the system. For example, suppose you have 1000 qubit system. Then you need to describe the system, you need to specify 2 to the power 1000 complex numbers. Now, in classical world, you don't have enough space in the entire observable universe to even describe the system. Whereas the system of 1000 qubits is very small. For instance, if you consider, as we said, one hydrogen atom's electron being in ground state or excited state as a qubit, 1000 hydrogen atoms forms a 1000 qubit system. And within 1000 hydrogen atoms, nature is playing with 2 to the power 1000 complex numbers. So this is massively parallel computation that nature is doing, which we can harness. In fact, we can harness that to break RSA or do integer factorization. So all of you are aware of RSA cryptography algorithm? So how it is depending on the fact that integer factorization is hard. So if all of you are not, some of you are, well and good, we can work with that also. If none of you are, even then it is not an issue. You should know what is integer factorization. So if you have n which is a product of two primes, let us say, the integer factorization problem is given n in decimal or binary, give me the product of prime form. So notice that fundamental theorem of arithmetic says there are many ways in which you can represent numbers. One way from fundamental theorem of arithmetic is you can represent a number uniquely in the product of prime form. You can also represent it in decimal. You can also represent it in binary. All these are different representations of the same abstract concept of the number. But sometimes it is easy to convert one representation to another, sometimes it is hard. So integer factorization problem is, if I give you a decimal or binary representation of a number, can you convert it to the product of primes representation of the number? In school, 5th class, you would have done prime factorization of numbers by hand for small numbers. But for large numbers, no efficient algorithm is known till date to prime factorize a large number. In the worst case, there may be some easy numbers to factorize, but in the worst case, if I give you product of two large primes, it's very difficult to find out what those two primes are. Based on this, there is a crypto system called RSA which works. But if you have a quantum computer, what we'll see now is we can actually break or find an efficient algorithm for integer factorization. So here is the algorithm. So 4 steps. First, the problem of integer factorization is going to be reduced to another problem, namely finding the non-trivial square root of 1. What it means by reduction? So a problem A is reduced to problem B if a solution to problem B helps you solve problem A efficiently. Okay? So we'll say that there is another problem called non-trivial square root of 1 modulo A. We didn't define the problem, we'll define it. Then we'll reduce it to factor. Now the problem reduces to finding non-trivial square root of 1. That step 2 says, if you want, you can reduce that in turn to the problem of finding the order of a random integer modulo n. So this is a randomness reduction. Here again we didn't define what is the order of a number, we'll do that. So what stays now is, suppose I want to factor a large integer. It is enough if I know how to find the square root of unity modulo of that large integer. If you suppose I want to find the square root of unity modulo of the large integer, it is enough to find the order of a random number. Alright, this is 2 steps. For each step I will have a slide to explain what that problem is and how to do it. Okay? How do you find the order of a random integer? Notice that the integer could be very large, the order also could be very large. Suppose you are able to set up a quantum superposition. So we said quantum superposition is lots of complex numbers. N qubit system can have 2 covariant complex numbers to describe it. Suppose these complex numbers are periodic, in the sense the amplitude is not zero exactly in arithmetic progression. So at t at say some a, then a plus d, then a plus 2d, and a plus 3d, a plus 4d. I mean, it is periodically not zero. Then notice that when I measure it, I will get only one element in this one index in this arithmetic progression. If I am able to set up a superposition such a way that this common difference d is turning out to be the order that I want, then if I get d from that, I will be able to factor the integer. So how do you get the common difference from a periodic superposition? Notice that if this a were 0, if it was periodic at d, 2d, 3d, 4d, 5d and so on, we know how to get it. How you measure, you will get a random multiple of d, you repeat this experiment several times, you will get several random multiples of d, take the GCD of all of that, GCD of several random multiples of d will be d with high probability and you got d. However, if the offset is not 0, then you will get a plus some random multiple of d, then again a dash plus some random multiple of d, then it becomes difficult. And therefore, what shows the scientists who discovered this algorithm suggested is that you do a Fourier transform of this vector, a periodic superposition. When Fourier transform, the offset disappears and the d becomes n by d, and therefore notice that once you do a Fourier transform of this, the offset disappears, you will get superposition of n by d multiples, then you do this GCD of several indices, you will get n by d, you know n, from that you can get d. And that will conclude this story. So, it turns out that the matrix for Fourier transform is a linear transformation, turns out to be a unitary matrix, and therefore nature allows that to be done in a quantum computer, and to top it all, it allows it to be done efficiently, and that will be the reason why quantum computers can factor large integers very quickly. So, step 1, we will give you 4 slides for each of the steps. For factoring n, we said we'll reduce it to the problem of finding a non-trivial square root of 1 modulo n. What do we mean by that? Notice that non-trivial square root of 1 modulo n means a number x such that when x square is divided by n, remainder should be 1. That is what is called as non-trivial square root of unity modulo n. What do you mean by square root of unity? And x such that x square is 1. That is called square root of unity. What is square root of unity modulo n? And x such that x square is equal to 1 modulo n. Modulo when you divide by n, remainder should be 1. What do you mean by non-trivial square root of unity? There are two trivial square roots, x equal to 1 and x equal to n minus 1. These two obviously will work. 1 square mod n is 1, n minus 1 square mod n also is 1. But apart from n minus 1 and 1, between 2 and n minus 2, if you find an x such that x square mod n is 1, it's called a non-trivial square root of unity. What the first theorem or slide lemma says is that if you are able to find a non-trivial square root of unity, you can factor n. Non-trivial square root of unity mod n, you can factor n. What the lemma says is a non-trivial factor of n is nothing but the GCD of x plus 1 and n, where x is the non-trivial square root of unity, and here is the proof for that. The proof is if x square is congruent to 1 mod n, that is x square when divided by n gives remainder 1, then notice that n must divide x square minus 1, but x square minus 1 is nothing but x plus 1 into x minus 1. But notice that x is not trivial, and therefore x is between 2 and n minus 2, and therefore neither x plus 1 nor x minus 1 can be fully divisible by n, because they are all smaller than n. A number smaller than n cannot be divisible by n. Therefore, when two numbers x plus 1 and x minus 1 are multiplied and each of them is not divisible by n, but the product is divisible by n, is only possible if some prime factors of n divide x plus 1, some prime factors of n divide x minus 1. Because n does not divide the whole thing, and therefore if I take GCD of either x plus 1 or x minus 1 and n, I will get a non-trivial factor of n. And this is the reduction. For example, if you want to factor 15, you find a non-trivial square root of unity modulo 15, say 4. So, because 4 square when divided by 15 gives remainder 1, and 4 is neither 1 nor 15 minus 1. Therefore, 4 is a non-trivial square root of unity. What this says is, therefore, GCD of either 4 plus 1 or 4 minus 1 and 15 is a non-trivial factor of 15. So, we have reduced the problem of finding this factor of n to the problem of finding a number x between 2 and n minus 2 such that x square when divided by n gives remainder 1. Finding a non-trivial square root of n. How do you find that? That is step 2. How do you find such a square root? That is step 2. How do you find this? Step 2. We said we will reduce it to the problem of finding the order of a random number. So what do you mean by order? So order is the smallest positive integer r such that x power r when divided by n gives remainder 1. Now if we take a random x and find its order, if the order turns out to be even, then x to the power r by 2 mod n should be a non-trivial square root. So for example, if n is 15 and if I take a random number 2 and find its order of 2 is 4, because the smallest number such that 2 power r when divided by n gives remainder 1 is 4. So order of 2 is 4, 4 is even, and therefore 2 to the power 4 by 2 mod n should be a non-trivial square root of unity, that is 4, and therefore the problem was now reduced to finding the order of a random number. How do you find the order of a random number? You set up a superposition such that it will be periodic and the period should be r. How do you do that? You set up a periodic function. So f of a is x power a. You want the order of x. F of a is x power a model. Notice that this will be a periodic function where the period will be the order of x because f of a plus r, f of a plus 2r, and all this should be same. So period of f is r. Now you set up periodic superposition by actually setting up all possible inputs in superposition, applying this function f, you get all possible outputs, you measure, it will collapse to things consistent with the measurement, everything consistent with the measurement will be periodic, because that's a periodic function. That's why you can set up a periodic superposition and then you take a Fourier transform of this and keep measuring it and take the GCD, you will get the factors of n, and this is how you can break RSA. So I'll quickly jump to the analysis. So notice that in the classical world, Fourier transform can be done using FFT algorithm, fast Fourier transform, which actually does divide and conquer with two recursive steps. Therefore you get T of n is 2 times T of n by 2 plus r n, and that will give you n log n. In the quantum world, you can superpose these two recursions. The two recursions becomes one because I can superpose both the FFT recursions in a QFT, and that will give me T of n is T of n by 2 plus r log n, which would give me a order log square complexity. Therefore, you get exponential speed up, right? So this is your QFT circuit, right? You put this algorithm together, you want to factor, you will get this as the code, right? So we started off saying that quantum mechanics looks to be interesting for users, interesting for designers, more interesting for scientists and so on. Then we said it is looks to be tailor-made for security purposes. We said how to do a quantum key exchange. We said that's a positive news. We said how to break RSA. That is a negative news. And then we said if time is there, we can speculate how the future will look like. Unfortunately, time is not there, and therefore we need not speculate. So we stop here for questions.
Thank you, sir, for your insightful and thought-provoking address. May I invite our resource. It is a privilege to honor our resource person, Dr. Kannan Srinathn, for graciously accepting our invitation and enlightening us with valuable insights. I request Mr. Praveen sir, Vice Principal sir, and HOD and DC, Dr. Basu sir, to present the memento as a mark of gratitude. There.
Any questions? All easy. Okay, so you have no questions. I have only one question. Did you understand anything or not? Total blank response. So if you did understand anything, don't worry. You can in the chat GPT age, what is there? You can find out all the answers from chat GPT itself when you are in doubt. So this session is like an exposure session. So there is something called quantum computer. It can do wonders. It can actually give you some cryptographic solutions. It can break RSA. You can also do several other things from there. If you know this, if and when you get interested in this field, you can read on your own. So notice that the existence of this itself, if you do not know or never heard of, then you will not think about it. Now you know that such things are there. Some people will be interested, some people need not be. People who are interested can read on their own with other help. So this is an expo session. Even if you didn't understand a word of it, no problem. If you just know that such things are there, it is enough. Thank you.
Previously, they don't know anything, sir. They know zero, sir. They are zero knowledge. Now they know some terminology, at least. For some quantum computing is there, they need to apply some quantum Fourier transformation is also there. They should know some words and terminology. This is very important. That's why I have taken my students. At least they should know the terminology and what's going on. They have to start the work now itself, at least. That's why I given it. Thank you, sir. Thank you. Yes, sir. That's why I taken my students.